Welcome to our video lecture on topic 5.3 bond enthalpy. Our essential idea for the day: energy is absorbed when bonds are broken, that's endothermic, and energy is released when bonds are formed, that's exothermic. Our objectives: we're going to define bond enthalpy. We're going to distinguish between those endothermic bond breaking processes and exothermic bond forming processes. We're going to describe relationships amongst bond lengths and strengths and polarity and this bond enthalpy stuff that we're talking about. We're going to calculate some changes in enthalpies of reaction using bond enthalpies of the reactants and the products. Then we're going to explain some of the differences in UV absorption by oxygen, molecular oxygen, and ozone bonds. So again, our essential understanding: energy is absorbed when bonds are broken and released when bonds are formed. This energy is known as bond enthalpy or bond dissociation enthalpy. What's interesting is that the values that we have for bond enthalpy are averages from lots of different molecules that have these different kinds of bonds. It's always going to be in gaseous state, so that's an important thing to consider. We're looking at a couple examples of bonds here and their bond enthalpies. So if I want to break a bond between two hydrogen atoms, this molecular hydrogen molecule, I need to add 432 kilojoules per mole. If I wanted to break bonds between chlorine atoms in a chlorine molecule, I would have to add 239 kilojoules per mole. If I wanted to make bonds between hydrogen and chlorine, I would actually release, because energy is released when bonds are formed, we would release 427 kilojoules of energy. That is a negative because it's exothermic, and we know that exothermic is a negative delta H. Interestingly, as the bond length increases, strength decreases. So a longer bond, and if we look at chlorine's a pretty big molecule, and so the bond between two chlorines is longer than the bond between two hydrogens, which is a very small molecule with small atoms. So this enthalpy, notice, is less than this enthalpy because hydrogen is shorter and therefore a little bit stronger. Polarity is also going to affect the strength of the bond in that enthalpy. The more polar a molecule is, the higher the enthalpy. Notice that this hydrogen-chlorine molecule is quite a bit stronger than chlorine because of the polarity. It's a little bit smaller because hydrogen is smaller than chlorine, but it is not significantly different from that hydrogen because this guy is so polar, and of course hydrogen is nonpolar. In order to calculate delta H of reaction, that enthalpy of reaction from our bond enthalpies, what we do is this. We're going to add the enthalpies from all the bonds that we have to break in the reactants, and then we're going to subtract, because remember that forming bonds is exothermic, that's a negative delta H. We're going to subtract the bond enthalpies in all of the reactants. So if I'm looking at this equation here, I need to break a hydrogen-hydrogen bond, I need to break a chlorine-chlorine bond, and then I need to form two hydrogen-chlorine bonds. So I need to add 432 kilojoules to break that bond. I need to add 239 kilojoules to break this bond, and then energy released. Energy releasing is a negative delta H. We're going to release 427 kilojoules of energy. Notice that I have 1, 2, so I'm going to multiply that by 2. Handy dandy calculator says that 432 plus 239 minus 2 times 427 gives us a grand total of negative 183 kilojoules. So this is going to be our delta H reaction, our change in enthalpy of the reaction from those bond enthalpies. Let's calculate enthalpy of reaction using bond enthalpies, the complete combustion of octane. Remember that octane is one of our organic molecules. It has 8 carbons and To fill up all of those 8 carbons, we need 18 hydrogens. It's combustion, so we're going to add molecular oxygen. Because it's complete combustion, our products are carbon dioxide and water. To balance this, I need 8 carbon dioxides to get enough carbons in my equation. I need 9 waters for all those hydrogens, and that's going to leave me with 25 halves in front of that oxygen. I'm going to leave it here instead of scaling everything up because I do want to do this per mole of octane. I don't want 2 octanes here, I only want 1 octane. So we're going to keep that fraction in there. So I know that I need to break some bonds in my reactants. Let's do that first. I'm going to go ahead and draw octane kinda sorta. There's 5, 6, 7, 8 carbons. We know that we've got hydrogens all around that octane. I'm not going to draw them all. You can pretend like those are all a bunch of hydrogens. So the first thing that I need to do is break some bonds between hydrogens and carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I need to break 18 carbon-hydrogen bonds. I also need to break 1, 2, 3, 4, 5, 6, 7 bonds between carbons. I also need to look at that oxygen. So I have 25 halves of molecular oxygen. So I'm going to break 25 halves or 12.5 double O's. Good. So now what I'm going to do is use table 11 to figure out the kilojoules needed to break all of these bonds in my reactants. So I'm going to use this table, carbon, and I'm going to go across to hydrogen. So carbon and hydrogen intersect at 414 kilojoules per mole. So I need 18 times 414 is going to be positive because it is endothermic bond breaking. I also need 7 carbon-carbons, and so I'm going to find carbon-carbon. That is 346. So again, positive because we're breaking those bonds, 346 kilojoules per mole of that bond being broken. Oxygen, oxygen, be careful. We do not want 144 because these are single bonds and we know that molecular oxygen is double. So I'm going to use this handy dandy list at the bottom. My double O's are 498. So I'm going to do 25 halves or 12.5 times 498. And again, that's going to be positive because we are breaking all of these bonds. So with our calculators, let's go ahead and figure out how much energy we need to add to break bonds. So I have 18 times 414 to break all the carbon hydrogens. We're going to add to that 7 times 346 kilojoules of energy to break all of the carbon carbons. We're going to add to that 12.5 times 498 to break all of those oxygens, and our grand total is going to be a positive 16,099 kilojoules of energy to break all the bonds in our reactants. Let's make some new bonds in our products now. So carbon dioxide is going to look like O-double-C-O, and then our waters, of course, are H's, O's, and H's. So I have 2 oxygen-carbon double bonds in each 1 carbon dioxide. So that means I'm actually going to have a total of 16 bonds because I have, again, 2 carbon-oxygen double bonds for each of those 8 carbon dioxides. So I have 16 of the C double O's. We also have in water, I have O's and H's. O's and H's. I have 2 of those in every 1 water. We have 9 waters. That is 18 OH bonds. Oop, that's a single bond. I made it look kind of double-ish. Good. Let's look at our table. Double O's. These are going to be double CO. In our multiple bonds here at the bottom, C double O is 804. So that's going to be a negative 16 times 804, or you could also call it 16 times a negative 804. We're going to get the same thing, right? And then our 18 OHs. OHs are going to be here in the table. OHs are 463. 18 times a negative 463, or negative 18 times 463. It's going to be the same thing. So how much energy is released when we make all these new bonds? 16 times negative 804 plus 18 times negative 463 gives us a grand total of negative 21,198 kilojoules of energy is released when we make those new bonds. at this point, you can kind of think about our potential energy diagram. If we had 16,099 kilojoules of energy to break all those bonds in the reactants, and then I have 21,198 kilojoules of energy being released. When we make the new bonds, we can see that we have an exothermic reaction. 16,099 minus 21,198 gives us a grand total of negative 5,099 kilojoules per mole for the complete combustion of octane. Feeling good? Good. Let's look at this reaction between ethine and steam. So we have two possible products being shown here. So this guy could be either A or B. And we are being asked to use section 11, which again is our bond enthalpy table, to figure out the enthalpy change for producing A. I'm going to take this guy here. So ethine, I've got C2H2. Ethine has that 1, 2, 3 triple bond between our carbons. Water looks like this. Ooh, that's an H. So I know that I need to break one triple bond. So I have positive 839 for that one triple bond between the carbons. My carbon-hydrogen breaking energy is a 414. There are 2 of those, so 2 times 414. And then in my waters, I have just that one water molecule, 2 molecules that I need, or sorry, 2 bonds that I have to break in that molecule. They're both an OH, and so that bond enthalpy looks like 463. So that's the energy that we need to add, 839 plus 2 times 414 plus 2 times 463 gives us a grand total of positive 2,593 kilojoules of energy needed to break all the bonds. Now let's make A. I'm going to use the picture A, not this guy, because the bonds are specific in the picture. So I see that I have 1, 2, 3 carbon hydrogens. So I'm going to do 3 times negative, because again, we're forming bonds, so it's going to be exothermic. 4 times carbon hydrogen is 414. We're also going to break that carbon double-double. That is 1 times a negative 614. I also have this carbon-oxygen single bond. That's going to be 358. That's very small. It's hard for me to see with my old lady eyes. I also have an oxygen-hydrogen here. Oxygen-hydrogen is going to be that 463. Negative because we are forming that bond. So let's add that all up. I have a negative 414 times 3 plus negative 614 plus negative 358 plus negative 463 gives us a grand total of negative 2677. So I'm going to take the energy that I need to add to break the bonds, 2593, minus the energy that is released when we make the new bonds, 2677, and our grand total is a delta H of negative 84 kilojoules. This is the enthalpy change for the reaction to produce A. We're going to release negative 84 kilojoules of energy is released. So for this guy, it was a negative 84 kilojoules of energy is released. To make product B, I'm releasing so much more energy. I'm releasing negative 213 kilojoules of energy is being released to make B. Since I'm releasing more energy, less energy is left in product B, which means that product B is more stable. More energy was released, so less energy is stored in product B. That makes it more stable. Less energy, more stable. Be careful. We learned a while back that if you want to find the enthalpy of reaction from standard enthalpies of formation, then we do products minus reactants. And here I'm telling you that with table 11 and our bond enthalpies, we're going to do add the reactants because it's an endothermic process, subtract bond enthalpies of the products because that is an exothermic process. All right, so now let's talk a little bit about ozone, and then we're going to wrap up this day. So Lewis dot structures for molecular oxygen. So I'm going to do my two oxygens. That's going to, remember, we have a double bond, and then there are those non-bonding electrons not in the bond on those two oxygens. For ozone, ozone is O3. This guy has that little bit of a resonance structure. So we've got some double bonding between our oxygens, but we also have a single bond on the other side in one of the Lewis structures. But of course, we've got some resonance, and so imagine that I'm drawing that with the double bond on the other oxygen. Determine bond length and enthalpies. So bond lengths are given to us in table 10. I see that bond length for double O's is 121. So 121 times 10 to the minus 12 meters. For ozone, you could think maybe this is 121 times 10 to the minus 12 meters, and that single bond OO is perhaps 148 times 10 to the minus 12 meters. But in reality, we know that there's some resonance. Those electrons are delocalized. They kind of go back and forth. So in reality, what we have is something between those two numbers. So maybe like 135-ish, I'm not sure, times 10 to the minus 12, because these aren't really like a single and a double. They're more like each 1.5 length bonds. So 121 for molecular oxygen, maybe 135-ish for ozone. Bond enthalpies is going to be the same idea. So our double O is here. This is a 498 kilojoules of energy that we would need to break the bond. 498 kilojoules of energy would be released if I formed that bond. For our ozone, again, it's going to be something in between the single 144 and the double 498. So be super careful. Don't assume that they are singles and doubles, but instead are 1.5s. This is going to help us understand ozone cycle, so formation and destruction of ozone. Notice that this molecule, O-double-O, which is a little bit shorter than 1.5 bond lengths, because we know that double is shorter than single and 1.5 is somewhere in between double and single. So notice that the energy required has a shorter wavelength. Shorter wavelength means higher energy. Higher energy is needed to break apart the bond in oxygen, molecular oxygen. If I want to break the bonds in our ozone molecules, because those bonds are a little bit longer and a little bit less energetic. So longer, less strong, less energetic. I don't need quite as low a wavelength. It's going to be a longer wavelength, which is going to be a lower amount of energy. Good. All right, so one more little bit, ozone and then chlorofluorocarbons. So we know that chlorofluorocarbons that we have in refrigerants and aerosols can be released into the atmosphere, and they can, in the upper layers of the atmosphere, get zapped by UV radiation. These chlorine-free radicals fly around, attack the oxygens, and then remember, we talked about this back in organic chemistry. We have our initiation step, our propagation steps, where those free radicals keep attacking each other until we run out of our hydrocarbons, and then termination steps start to step in. But a lot of our ozone can be converted into molecular oxygen, but then that chlorine-free radical is released to go and destroy more ozone. So a little bit of CFCs goes a long way for ripping apart our ozone. And we don't want ozone close to where we breathe because it is considered a pollutant, but up in those upper layers of the atmosphere, it's really good at blocking UV radiation so that we don't all get skin cancer. So protect the ozone layer. We did it, my friends. We know that energy is absorbed when bonds are broken, released when bonds are formed. We talked about bond enthalpy. We know that bond breaking is endothermic and bond forming is exothermic. We talked about how longer bonds are less strong bonds and therefore have lower bond enthalpies. More polar bonds are stronger and therefore have higher bond enthalpies. We figured out how to calculate enthalpies of reactions from bond enthalpies. We're going to add the energy that is needed to break the bonds in the reactants. We're going to release, that's a negative delta H, the energy of the bonds that are formed in the products. And then we talked about oxygen. That's a double bond, short and strong. Ozone, that's kind of like 1 1/2 bonds. Those are a little bit less strong, a little bit longer than the molecular oxygen. We did it. Good work.